Hello, everybody, and welcome to the monthly NNCI webinar series. My name is David Gottfried, and I am the Deputy Director of the NNCI Coordination Office at Georgia Tech. This is a monthly webinar series that NNCI started recently with topics varying among the different topics within the NNCI, including education and outreach, societal and ethical implications, computation, and innovation and entrepreneurship. And this is in that latter category. Before I introduce my colleague Matt Hull to introduce today's speaker, I just want to make you aware of the next webinar, which will be on June 23rd at 4 p.m. Eastern Time. And that will be another computation talk with Professor Frank Register from the Department of Electrical and Computer Engineering at the University of Texas at Austin. And that you can find all of the information about the webinars on the NNCI website under the events page. And so now I'm going to turn it over to Dr. Matt Hull of Virginia Tech, who is the NNCI Associate Director for Innovation and Entrepreneurship. Go ahead, Matt.
Thanks a lot, David. And thanks everyone for joining us. It's a pleasure to be with you. This is really my first time operating in an NNCI capacity. You may recognize me from some of the work I've been doing at Nano Earth at Virginia Tech. But fortunately, during the renewal, we're now addressing the innovation and entrepreneurship component through the coordination office as well. So my role as AD for innovation and entrepreneurship is to help develop the NNCI innovation ecosystem. And we have a specific emphasis there on engaging with industry and fostering an infrastructure that enables and supports diverse entrepreneurs who are developing nano-enabled solutions for societal needs. The I&E, or Innovation and Entrepreneurship Speaker Series within the NNCI Speaker Series, is really focused on one component of developing that ecosystem. In the future, we anticipate that some of our I&E speakers will be selected through the I&E working group that will be established as a part of our I&E efforts. A little bit of background on this particular component of the speaker series is we started doing this at Virginia Tech as a way to engage more industry users. We found that by bringing in industry speakers who had specific challenges they were working on, maybe they were non-traditional users, they had no idea about our facilities, but we were able to bring them in, have them share a little bit with us about the challenges they encounter in their industry, and then we would reciprocate with some of the solutions that we offered industry. And through that, a dialogue would be established and a relationship would be built. And we had nearly 100% of our industry seminar speakers become users of our facilities. So it's a part of a strategy for engaging folks in industry. If you don't have trouble getting industry users, then we'd welcome your feedback on how to go about doing that, but it can often be a challenge. And so we found this as one approach towards doing that. So the focus of these talks is really on understanding industry needs and trying to meet at this interface between industry and academia. We know how the talks can vary, and as academics, we can expect certain things from talks, and then as industry representatives, we can expect certain things from talks. So we're trying to meet at that interface and listen to one another and hear about challenges and solutions offered at that interface. And so with that, a little bit of background on the innovation and entrepreneurship component of the NNCI seminar series. It's my pleasure to introduce to you our first innovation entrepreneurship series speaker, Terrance Barkan. He will be talking about 2D advanced materials and U.S. national priorities. I thought Terrance was a great speaker to kick us off, given the breadth of graphene's impact in nano communities. And I'm sure there's every node within our infrastructure is probably working on some graphene-related project. And so it's the type of, the scope of Terrance's work is certainly something that impacts all of us. Terrance's background, so interestingly, Terrance and I really hadn't met before COVID. So recently COVID brought us together on a mass project, and we've been working on that. And through that, I thought, Terrance might be a great person to chat with us. And so for more than 30 years, Terrance has been building trade and professional organizations on a global basis. He has a certification. He's a certified association executive, which means basically I think he has his PhD in building these types of complex organizations that really have a lot of challenges in terms of balancing the needs of their stakeholders and representing them on important committees and things of that nature to help make sure that their organizations are growing and being supported as they need to be. He's worked in more than 70 countries on 6 continents around the world, developing and implementing association growth strategy projects. And under, most recently in 2013, Terrance founded the Graphene Council as a global trade and professional community connecting scientists, academics, producers, end users, and commercial professionals with an interest in graphene. And so the mission of the Graphene Council is really something that we're going to learn a little bit from Terrance about today. So with that, Terrance, I want to thank you for taking time out to chat with us. I want to thank all of our listeners online for joining us, and sit back and we'll listen to what Terrance has to say about graphene. Thanks a lot, Terrance.
Thank you, Matt. Thank you very much. Appreciate it. And David, thank you. And I know you and I have met a number of years ago, and it's been amazing to see how this field has progressed with not just graphene, but with other 2D materials, and a tremendous amount of work that's done in academic institutions everywhere. So let me just briefly go through, kind of take you through current state of the art with graphene materials and what's happening. As Matt said, the Graphene Council, it's a trade and professional body for the graphene sector. So that means all the way from raw material suppliers, that means graphite miners to graphene producers and everybody in between, up to the customers, including companies like Ford Motor Company or major chemical companies like BASF and others. In total, we reach 30,000 material scientists worldwide, and I would encourage anybody who has an interest in graphene or the other entity that I'll talk briefly about today, and that's Maxine, so Max Phase Materials, an association we just launched a month ago with Drexel University. If you have an interest in any of these 2D advanced materials, please reach out, because we have a weekly newsletter that gives updates on research updates, commercial developments, and patent filings worldwide. So it's really quite comprehensive. And to give you an idea of some of the members we have, this will populate. Sorry, it doesn't show everybody here. There's a lot more, but these will come in. We, as you see here, just kind of examples like Manchester University, where graphene was first isolated, and then some of these major company names that you'll recognize, even Turtle Wax. Recently, a 75-year-old traditional company has come out with a line of graphene enhanced wax products as their premium products. So it just gives an example of how this is becoming commercialized. And one of the things that we do as the Graphene Council is we produce something called the Graphene Report. This is about 600 pages that cover production methodology, characterization techniques, and everything else, just to give you an idea of just how comprehensive the area is that we cover. To kind of cut to the chase on the commercial side of it, today there are already about 300 companies that claim to produce graphene, and I say claim because there's a big difference between bench level prototyping and actually commercially available volumes. Of those 300, we feel that about 100 of them are what we would call commercially mature, so they're producing, material that could actually be sold. And of those, there's about another 70 that are really proper commercial companies in the graphene space, which is not an insignificant number of companies for an area where a material was just uncovered about 15 years plus ago, which is, just a baby in terms of materials life. And then the largest producer right now is a company called Nano Explore, which happens to be in Canada, with 4,000 metric tons per annum capacity going to 10,000. But we have companies that are not yet in the public sphere that have identified capacities at the 15,000 per metric ton per installation phase. So we see a potential rapid ramping up of material. And this is important because a lot of the spin-out companies that come into this space come out of academia. They're university spin-outs, or they're graduates who start their own companies in this sphere. And if there's anybody who's interested in doing something like that, or seeing your research work end up in a commercial sphere, we have some observations that we can share with you about some of the challenges you might face and how to overcome those, because a lot of graphene originated and continues to originate in the university production setting. If you look at graphene production methodologies, typically it's been graphite to graphene, so exfoliation methods or CVD, chemical vapor deposition, using carbon-bearing gas and creating crystals that way. But there are all sorts of production methodologies, including something called laser-induced graphene, excuse me, flash graphene, applying electrical current to carbon-bearing content, biofuel byproducts. We have one of our member companies, which is massively scaling right now, uses what they call a detonation method by combining acetylene with oxygen, igniting it, and the byproduct is a pretty pure grade of graphene. So it's fascinating that there are many different routes to end up with this graphene material, which is, I neglected to say what graphene actually is. It's a single carbon layer of sp2 bonded carbon in a crystalline form. And according to the ISO definitions, that includes not just the single layer variety, but 2-layer, 3-layer, 4, up until 10 layers of carbon, and also graphene oxide or reduced graphene oxide. And then this material can also be further manipulated through functionalization or enhancement by adding different species or molecules to the edges or the surfaces of these materials. And we see really interesting things, graphite companies trying to go up the value chain and create graphene. We see no less than 4 different petroleum companies have contacted us trying to figure out, in this world where every automotive company on the planet literally has said they're moving to all electric either by 2030 or 2035 or 2040, but they're all headed the same direction. So now petroleum companies are kind of interested, what do we do with that part of the distillate stack? Can we make graphene out of it? And as this market matures, it's still nascent, but it is maturing rapidly. We see graphene companies, some have the customer, but they don't have the product. Some have the product, but they don't have the customer. Now we see collaboration. So it's quite typical of a turbulent new industry. Just to give you an idea of what is happening, this is a short period of time between January and April of this year to show what kind of fundraising has taken place, even when the environment is actually not that favorable. Some people got quite excited about graphene when it was discovered in 2004. They got really excited when the Nobel Prize was awarded, and it stimulated a lot of interest. And then reality kicked in. As the famous Mike Tyson quote, everybody has a plan until you get punched in the face. Everybody had great hopes for graphene, but then reality set in and how difficult it was to produce it. Well, we've overcome a lot of those difficulties, and now we're back on the commercialization track. So just to give you an idea, here's a short synopsis of all of the different application areas, or a number of different application areas where graphene has real world proven ability. And so on the left side of the columns, we list the application area like 3D printing, aerospace, automotive, etc. And then we talk about type of graphene between bulk and monolayer. And without going into too much detail, because this isn't a dissertation on what graphene is or the types, but you have monolayer graphene or single layer graphene, which behaves in a certain way and is very suitable for certain applications. And then we have what we call bulk graphene, which is the typical black powder or multi-layer material, which is suitable for completely different applications in many cases, and in some there are crossovers. But you might as well treat these as 2 very different materials because the production methods are different and the markets tend to be different. The areas where graphene is getting a lot of traction commercially right now, energy storage, so battery technology and chemistries, surprisingly cement and concrete, because when you add graphene to concrete, you can increase its strength, but equally important from a commercial perspective, you can reduce the cure time, so you get to the target strength rate in 7 days instead of 28 days, for example. So that has huge economic implications. Coatings, elastomers, And then on the sensing technology, especially for biomedical sensors, so looking for new biomedical sensing that is much more sensitive, much more selective, much faster, and has a smaller footprint, for example. So again, if you compare medical sensors with concrete, you couldn't be more diverse. Just to give you an idea on the energy technology, the energy storage side, you see obviously here a list of companies who have made their declarations of when they're going all electric. And it's not just the car manufacturers, but it's those large fleet owners. For example, excuse me, the U.S. Postal Service or FedEx or Uber. And so every one of these entities is racing for the same resources, and that means much higher energy density and new technology, because the existing legacy lithium-ion battery technology will get you so far, but not where these companies need to be. And then let's go to volumes. If you look at and make the assumption, and these are just rough assumptions, but they're reasonable. About 1 kilowatt of energy requires 1.25 kilograms of anode material. If you look at a passenger vehicle, for an electric vehicle, it needs about 70 kilos of anode material. That anode material can have a range of content of graphene from 1% approximately to 15%. And that would be 875 metric tons to as much as 13,000 plus metric tons of graphene per 1 million vehicles. The global production volume for passenger vehicles is approximately 90 million today. That can change and will change. It's constantly growing. And that means we need somewhere between 78,000 and 1.18 million metric tons of graphene on an annualized basis just for new car production. And if you'll remember to my original slide, the current capacity is at 10,000 metric tons globally. So there's a huge gap. And the challenge with these interesting technologies is once one of these applications, if it were just batteries, the demand would far outpace the production capacity as it is today, even with a small, 3 million a year or even 1 million a year vehicles. Another application area that's quite exciting, as I mentioned, was concrete and cement. Every metric ton of cement that is produced, so you bake that material, you produce approximately 900 kilos of CO2. So it's almost a 1-for-1. When you make cement, you make CO2. That's about 92 kilos of CO2 per metric ton of concrete, because the cement is diluted with aggregates into the final concrete product. So 92 kilos of carbon tend to find their way in every metric ton of concrete. Concrete is used at a higher volume than any other material on the planet, with the exception of water. Adding graphene to concrete improves compressive strength, flexural strength, and reduces the cure time, which is hugely valuable. And it can be as little as 30 grams of material per metric ton. And we now see graphene approaching price points at $50 a kilo or less, which means it's just $1.50 per metric ton of concrete. And yet, because you can reduce the concrete composition the cement composition in the concrete, you can remove somewhere between 9 to 10 kilos of carbon per metric ton. So the graphene not only strengthens it, but it allows you to have CO2 reduction, which is incredibly important as one of the top priorities globally, not just in the US. Just to give you an idea how many companies on the left are companies that produce graphene or are working with graphene applications. And in fact, this week, there was a concrete slab laid in Manchester that eliminated the need to have rebar in the concrete. So that's another cost savings by being able to remove that. And on the right-hand side, you see some of the entities that are looking at how to use this new innovation. 200 grams of graphene per dry metric ton in just 1% of global cement production is 1.64 million metric tons of graphene. So even at just 0.1% market penetration globally is 164,000 metric tons per annum just for this one application. And it would take out between 3.7 to 37 million metric tons of carbon per annum. So again, this is an example. If graphene is seen as a viable ingredient, even at an incredibly small penetration rate, we need enormous volumes. And so that's the interesting pull. I mentioned turtle wax, and I have that product at home. Two different car companies, two different continents, both came up with a similar solution independent of each other, which tells me that graphene works on its own merits. It's not just a marketing gimmick. And nanoceramics are really popular for barrier properties right now. And graphene is seen as being superior in performance to nanoceramics, giving better barrier properties, and it also blocks UV rays. And depending on the type of graphene you have, it is transparent, at least 98.2% in the single layer kind. So that's another example. Another example, just to give you some tangible examples, is coatings. If you think of the merchant marine area, a tremendous amount of expense is paid when the ships go into dry dock, and that's because they're rusting, they need to be repainted, or the hulls have been fouled by bioorganisms. And so if you can have a better coating that reduces the frequency of a ship having to go into dry dock, where it is not earning anything and it's costing the owner, that is hugely valuable. And we see there again, something above 10,000 metric tons per annum in terms of capacity just for that one very narrow niche market of marine coatings. And then I want to give you a different example of a different type of graphene, and this is quite exciting. There's a company called Paragraph, and these companies, of course, are members of the Graphene Council, that produce monolayer graphene, which is a single atomic layer of carbon. And to give you an idea of what that means, you could cover 2,360 square meters of surface area with 1 gram of graphene at monolayer levels. So it's tremendous surface area. So they make sensitive Hall sensors, Hall effect sensors, that they're prototyping and testing with CERN because they're in a very corrosive, high temperature, high pressure magnetic environment that they have to operate in, and they find that these materials work better than anything else so far. Another company that makes these kind of materials, CVD graphene, is a company called Graphenia, which is based both in Spain and in Boston in the US. And they actually have developed a foundry service. So if you had a design for a circuit or a device that you wanted to make out of graphene on a wafer, instead of having to purchase the graphene and then make the device yourself, you can give them the design, they'll make it for you, and then you pay on a per device basis. So you can get several customers that actually share a wafer, reducing the cost, and you just pay on a per device basis. I think it's quite innovative, not just from the technology, but I think the business model is also incredibly interesting because it's taking the friction and the obstacles away from the customer. I think it's quite clever. The Graphene Council in 2020, just a few months ago at the end of the year, performed a survey of the global community. We had over 800 responses from 65 countries. So we have a really good set of data. And that report, by the way, you can access for free. We can give you a copy for free. I'm just going to talk about some highlights. This diagram here should give you two distinct pieces of information. One, you see the different types of materials. So graphene is not one thing, but many things. And then also what's quite interesting is functionalized graphene and graphene oxide are at the top of the use in terms of frequency of use. Almost half of all respondents are working with these types of materials. We did this survey several years ago, and it was graphene nanoplatelets or flake graphene that was at the top. So that's shifted. Graphene oxide, by the way, is hydrophilic. Graphene normally is hydrophobic. So that's another interesting dichotomy with the same kind of material. Because of the oxygen content, it becomes hydrophilic. This is just a question about some of the main things that are important to the industry. So measurement and characterization methods of graphene is at the top of the list, which is an indication that we still are also early in the adoption phase because we're still figuring out how to measure this stuff. Health and safety is important. And fortunately, graphene has a pretty good health and safety profile as a pure carbon and in its nanoplatelet form, as opposed to something like carbon nanotubes, which are fibrous and have a different health profile because of that. And then there's other issues like quality standards for batch-to-batch production, the defining grades or types of commercial graphene materials, which we are actively involved in defining right now. We're also involved in the standards with ISO, ANSI, ASTM, IEC, BSI, all these standards bodies we're involved in. And then at the bottom is interesting, establishing reference price data for commercial graphene sales. Graphene production and sales are not at a commodity level yet, and so pricing is not very transparent, and it's also not a high priority. So I want to show you, this is interesting because it's very rare in our lifetimes, and I would argue anyone's lifetime, to really be at the front end of an industry. And graphene, which was only discovered in 2004 formally, and I know some of you may be aware that there was actually graphene before that in different forms, but it just didn't get acknowledged. But the ability to produce this stuff at a lab scale was the first step, then to go, excuse me, from grams to kilograms, quality from batch to batch, get up to a production plant where you can make a metric ton of this stuff, and then figure out who in the hell are you going to sell this to, right? We need to know who are the end users and markets for this. And it's not like there were ready markets. People didn't understand the material, and also it wasn't understood what it could be used for. So understanding and getting the right price and volume and making investment in plant when there are no customers, educating customers, and then we get into the regulatory realm where it starts to get registered under REACH in the EU or with TSCA here in the US under EPA and health and safety concerns. And then finally, it gets adopted, just like carbon black is used every day, just like many other industrial materials are used every day. And this is kind of where we find ourselves today, is in this little red box where we're identifying markets, we're actively involved in that, we're doing price discovery, we're educating customers, we're engaged with regulatory agencies, we're conducting health and safety, and quickly we will be in the industry adoption phase fairly soon here, I expect. And this is another way, and actually we contributed to an article in Nature. We were invited to write for the 15th anniversary of graphene, an article for Nature, and we talked about the hype cycle and the evolution of graphene from, if we take 2004 as the date, 2010 Nobel Prize is awarded, and then there were tens of thousands of research papers, patent filings, companies being formed, companies going public. And where we find ourselves after people were disappointed that they didn't hit the El Dorado is we now find ourselves where graphene is much better understood. It's being produced at commercial volumes. It's getting into actual products, and it has real commercial utility. And now we're just simply in the natural adoption curve, which again, if you looked at the volumes I spoke of earlier in the tens, hundreds of thousands, over 1 million metric tons per annum for different applications. And then if you take all of those together, we're talking about multiple millions of metric tons of a material that you typically use at load factors of less than 1% by weight. It's just mind-blowing, at least it is to me. So graphene today has been tested and proven to work effectively in multiple applications. It's no longer a question, does it work? We know it works. And within just the next several years, 3 to 6 years, we're easily looking at about 300 to 700,000 metric tons of demand for this material. And we, as I mentioned, we also see different production streams, including from biomass materials. So taking things like hemp or other bio waste or wood products, creating products out of it and having graphene as one of the byproducts is really interesting. That's my presentation. I really appreciate your attention. I'm very interested to see what questions you all might have. I hope this was somewhat enlightening. And I did mention early on that we formed the Maxine Association. So those of you who might know what max phase materials are, they're transition metals that are also scaled at the atomic level. And there's another set of materials called transition metal dichalcinides, TMDCs, which are also 2D materials. The future is we are going to have hundreds, if not thousands, of two-dimensional, from the atomic level up, built materials. And that's incredibly exciting. And I want to close my statement with this. If you look at the major problems that the world is facing, CO2 reduction, infrastructure resiliency, expansion into space, the need for renewable energy, and with that, with all the renewables, we need energy storage devices because the demand is unpredictable. These are all going to require a new class of materials that can do things we cannot do with traditional materials. And increasingly, it's clear that we're building from the atomic level up to tailor materials to have extraordinary performance that they don't have at the macro level. And so anybody who's interested in that kind of work, I think you have a long and bright future ahead of you. And what we try to do as a Graphene Council and the Maxine Association is kind of connect the dots, put people who study this stuff, understand it, together with people who can use it. And with that, Matt and David, if you want to, I can stop sharing, and let's take some. Hopefully, there's a question or two.
Thanks a lot, Terrance. That was great. I really appreciate it. It was also nice to see characterization as one of the top needs expressed by the survey respondents. So, David, do you have questions that have been submitted through the chat, or?
Yeah, do you see the Q&A?
I do. I see a couple questions here, so I can just read these. Is that
Sure.
Okay. So the first question is, I was wondering if Georgia Tech, as a university, is member of the Graphene Council, given the number of researchers here who work on
it. Not yet, but they should be.
Very good. Short and sweet. Maybe, so in terms of your university membership, can you comment generally on sort of what your representation of industries relative to academic units is?
Well, we have had a bias towards commercial entities because we're focused on the commercial adoption of this. We do have a lot of folks. I mentioned we reached 30,000 material scientists, 10,000 of those. So these are people who subscribe to our newsletter, for example, are in academia, right? And we also understand that there are usually more financial constraints or bureaucratic constraints, but we do have organizational memberships for research institutions. And there are several key benefits that I would say are open to these universities. One, that means every student and every member of faculty has access to the information that we provide. Okay, so that's one. Second, a lot of these universities have technology transfer offices that have a very wide portfolio, but we can certainly help them with their technology exploitation related to graphene and other 2D materials, right? So if they have a patent portfolio and they want to know which of these is most likely to be commercialized, we can help advise them on that because we work with the other end of the buyers of them. So those are just a couple of things. And we, of course, can point people to universities that have robust testing programs. The third thing is we do a verified graphene producer program. We do characterization work. When I say we do characterization work, we don't have our own labs. We depend on competent partners. And for example, with the graphene classification framework that we're doing now, we know that's going to drive more measurement requirements because people will need to have their material tested and declared what type of graphene it is. So those are just a few reasons why I would encourage, and we really welcome universities to work with us because we think we can add a lot more value than just what the membership fee represents.
Excellent. Let's see, next question I have here is bulk graphene a marketing term for thin graphite?
If you're a bad actor, yes. It can be. Bulk graphene, well, sorry, I should say bulk graphene is a term we use, and that just means multi-layer graphene, okay? And the definition for graphene under ISO standards is from 1 to 10 layers is graphene material. The problem is we do have companies in this field because graphene has got a cachet to it and a marketing value. There are companies that are producing and selling material that is not graphene. It's thin graphite or nano graphite or micro graphite, but they call it graphene. And the problem, of course, is that most customers who receive this material do not have the equipment or the expertise to verify what kind of material they have. We think increasingly that as more companies use this material, they will be the ones driving the testing, because for quality control, as they receive material in, they're going to want to verify that it meets their quality specs. They're not going to trust just what the producer says without validating it. So I appreciate the comment. There are people who take advantage of this material and its marketing cachet. And that's one of the things we work really hard on, is to make sure we deal with people who actually produce graphene and we represent it appropriately. Good question.
Excellent. Let's see. One more question that we have on the Q&A is, could you comment on why graphene aids with concrete formation, especially with such trace amounts per volume?
Yeah, it's an excellent question. And I'm not an expert in concrete, but my understanding is the chemistry of concrete, as old as that material is and as much as people work with it, it still remains a bit of a mystery on all of the crystallization processes that go on within that mixture. But we believe it's acting as there's two things. One, it acts as a nucleating agent, right, is this nanomaterial, because you can use other additives in concrete to improve strength and also to accelerate the cure rate. But graphene seems to be pretty unique because it has an incredibly high surface area. It seems to act as a nucleating agent for the crystallization process. And the other thing we found, which I didn't mention, is it's good at stopping the microcracking. Because what we found, and this is true not just for concrete, this is true for thermoplastics and thermoset composites, is that when the microcrack comes up against a graphene flake, because of the strength of the bonds in the graphene, it tends to stop the microcracking. So, for example, there is there are some hydrogen fuel containers, composite materials that we've seen that are using graphene because it blocks the hydrogen as a barrier property, but it also prevents microcracking, especially for use in space where you have these extreme temperature shifts and harsh conditions. And so some of that mechanism is applicable for concrete as well. I hope I answered your question with that.
Yeah, that's a great answer. I have a question here. I'll try to post it in here as well. I can answer them, but I got to figure out how to post them. But so I'm really interested in this academic industry interface, and I just wondered if you could comment on some of the specific challenges that you and your stakeholders have worked on, maybe where you've engaged with academia, what kind of experience you've had, what kind of challenges, and even success stories that you've had there. Can you comment on that? Somewhat of a general question.
No, I think it's a really good question. One of the general observations I will make is that you can be technology push oriented, or you can be commercial problem solving pull oriented, right? And so what I mean by that is there is so much you can do with graphene. We've seen a lot of people come up with different applications and say, oh, hey, look, we can do this motion detection device using graphene material. Well, that problem's already solved with other technologies that are proven, cheaper, easier, right? So I think one of the big challenges for academia, on the one hand, blue sky research is fantastic because that's how you come across innovative new things. But just because you can do something doesn't mean it's going to find a commercial market or be exploited that way. You have to be clear what problem you're solving, and your problem needs to be a pretty high value problem because there's switching costs, there's risk aversion. Customers will not try a new material just because it's unique. They'll try it if it solves a problem. It's got to be faster, better, cheaper, etc. So I think one of the biggest mistakes a lot of the spinouts from universities make that I've seen is they get enamored with their science and they get enamored with their technology, and they lose sight of what problem are we actually solving and what legacy materials are we competing against, right? So, you have to be pretty clear-eyed about that to clear all those hurdles. Otherwise, what you're going to end up doing is wasting a bit of time and money, and then you're back to square one at the end. So, I don't want to sound discouraging, but I can't tell you how many times I've seen people pushing water uphill. It's just it's great science, it's fantastic science, it's hugely brilliant, but it has no commercial application, or it's not sufficiently different from existing solutions to compete.
Matt, this is David. Can I ask a question as well?
You bet.
Thanks, Terrance, for a really excellent presentation. You mentioned toward the end that you expect about a demand of about 300 to 700,000 metric tons per year, really by the next 6 years or so. Is there supply to meet that? Or will there be supply to meet that?
I mean, it is the chicken and the egg question, but, can there be supply? Absolutely. If you think of, okay, so one of the traditional routes to production is graphite to graphene. Graphite is in ample supply worldwide, although the battery technology is going to suck up a lot of that. So there is going to be more demand for it. But there's a lot of latent graphite mines that are not in production today. These are near surface mines, so they're easily accessible. We have producers coming online that are targeting prices for graphite in the $400 to $500 per metric ton. Today it's about $1,200. Huge volumes. And that's just if you go graphite to graphene. Then you can do all the bio, right? And so there's biodiesel producers, that are going to have tens of thousands of production per facility where they're producing biodiesel. Then you have biomatter conversion. And then you have the traditional petroleum companies that are going to lose all of their gasoline production. Well, a lot of it, it'll take time, and they're going to look for new products so they can divert. So basically anything with carbon content. There's a big project in Utah to convert coal to graphene, right? So take the carbon content and have a process for conversion to graphene. Why? Because the demand for coal is going away. So I'm really confident that there's going to be tremendous, and I mentioned the other process, acetylene and oxygen converted to graphene. So there's many different production routes. There's a whole bunch of people looking at how to produce graphene. I don't think supply is the choke point, is my short answer.
Great, thank you.
Ask the flip side of that question, which is, I remember it was actually a few years back, some folks were talking about Ford Motor Company, an executive referring to the composite of the future was actually aluminum. It sounds like with, are companies like Ford getting more innovative and more willing to consider the integration of graphene composite materials in these? I mean, you look at something like the F-150, it's incredibly risky for them to deviate the way they've been making that truck for years. Yep. Can you comment on that?
Well, Ford happens. I can share public information. There's some non-public information that I can't share, but Ford is a member company in the Graphene Council, and they're one of the early innovators where they use graphene enhanced polyurethane foams in the automobile. The original intent was to improve the heat performance in the engine compartment with this material. But what they found is they got a dampening effect and a noise reduction on top of it. So now they're looking, where else can we use this graphene material to improve the ride of the car, the passenger experience, the longevity of the materials. They're even looking at its antimicrobial properties because graphene can be integrated into fabrics. Long story short, within the Graphene Council, we have no fewer than 50 different engineers from Ford who are actively engaged with us from South America, Europe, North America, et cetera, who are all looking at innovative ways of using graphene. And I would say they're one of the leading companies that are really looking at these advanced materials to unlock new performance levels. So absolutely. I mean, the amount of interest in this is amazing. You know, it's taken a while to get to this stage, but on the demand side, we have, and again, I can't disclose all of this because a lot of this stuff's under NDA, but we have companies that are engaged with us to explore how to use graphene in their products across their product lines. So think of chemical companies, plastics companies, because they're seeing not, a 5%, a 10% improvement. They're looking at 25, 40, 50% performance improvements in nylon 6, right? Or PA6 nylon. Graphene got a 400% strength change. It's insane, some of it. So the question then is begged, do you need nylon 400% stronger or not? That's a different question. But yeah, it's I think on the demand side, nobody wants to be first. Everybody wants to see somebody else kind of break their head and try something out. But as soon as we get these early adopters like Ford, like some other companies, and we have one other company putting graphene materials into the cathode, less than 1%, and they're getting a 50% energy density improvement. That's phenomenal for batteries. So, anyways, I could talk about this all day. I get very excited.
Well, it's good to hear. I mean, it's good to hear that the performance is driving some of the demand. Let's see. One other question popped in. What are the main differences and properties between reduced graphene oxide and graphene?
That's a really good question. So, graphene oxide is a material that has about 35% oxygen by weight. Reduced graphene oxide is what it sounds like. You take a graphene oxide and then you reduce the graphene. You can do that with light or heat or some other processes to remove the oxygen. You're left with reduced graphene oxide, typically at 5%, but you can get below that. Some of the biggest differences between then the reduced graphene oxide and if what we mean by graphene is either single or few layer material like graphene nanoplatelets that has no oxygen in it, there are not a tremendous amount of differences in terms of a lot of the performance factors. Here's where the difference is. Graphene oxide, because it's hydrophilic, can be put into a solvent and then spray coated, and then you could reduce it, right? So now you put it into coating, you put it onto a surface, and then you reduce the oxygen. And you go from a material that is hydrophilic and not electrically conductive, because the oxygen makes it an insulator and not a conductor. You reduce the oxygen, and now you have a conductor again. So there's all sorts of things you can do with putting that into patterns to make circuits, or to put it on a surface that you otherwise could not apply graphene to, the bulk graphene. So yeah, that would be some of the difference. And the chemical composition will be different. The performance factors will be different. The size and morphology will be different. But those are maybe some of the main comparison points I would suggest.
I think that's all we have here. So we've got 8 minutes left, but I think I see all the questions have been addressed. And if there are no further comments, Terrance, I would just like to thank you again for joining us. I think it was I don't know, you've got a great perspective dealing with a lot of these different stakeholders in graphene. There's a lot of myths out there around graphene. I think it's misunderstood in some communities. And so it's very helpful to have you on with us today to talk through some of those. Thank you so much.
Well, I appreciate this opportunity. I'll send you a copy of my slides, Matt. If anybody wants a copy of that, they can have them. And really encourage anybody listening that if you're interested and you want more information, do reach out, and we're always open to engage.
Great.
I'll just add my thanks as well, and hope to see everybody at the next NNCI webinar on June 23rd. Thanks, everybody. Bye.
Thank you.